When we think about electricity, our minds usually jump to circuits, wires, current, all that stuff. But today, we're going to look at it from a totally different angle. Think of it like an invisible landscape, a world of energy with hills and valleys all around us, created by electric charges. And we're going to explore it with a really powerful analogy. All right, to kick things off, here's a little puzzle for you. What on earth does a roller coaster have in common with a lightning bolt? I mean, one is this engineered thrill ride. The other is just raw natural power. They seem like they're from completely different worlds, right? Well, it turns out they share a really fundamental secret. The answer? It's all about stored energy. Yep, both of them are just these spectacular releases of potential energy. Think about it. That roller coaster sitting at the very peak of the track and the charges separating inside a thundercloud, they're both just waiting, holding onto all this energy, ready to unleash it as motion. And that idea, potential energy, that's the key. It's going to unlock everything for us today. Okay, so to really get a grip on this whole invisible world of electrical energy, we've got to start with something familiar, something we all just get. We're going to start with a simple hill. I mean, just picture it. You lift a ball, you push it up a hill. You're putting in work, right? You're fighting against gravity the whole way. But that effort isn't just gone. Nope, it's stored inside that ball as gravitational potential energy. The height is basically a measurement of how much energy you've packed in there. The higher you go, the more energy it's got, ready to be released when it comes rolling back down. Makes perfect sense, right? All right, you with me? Let's take that really simple idea of a hill and use it to step into the invisible world of electricity. We're going to build this analogy step by step. So you might be wondering, why does this analogy even work? I mean, gravity and electricity? Well, it's because the force between charges behaves almost exactly like gravity. As this quote points out, they both have this inverse square thing going on, which just means they get weaker with distance in the same predictable way. And that makes the electric force what physicists call a conservative force. That's just a fancy way of saying that any work you do against it gets stored. It's not wasted. And that is the magic key that lets us map our simple hill directly onto the world of electricity. And here it is. This is basically our Rosetta Stone for translating between the two. Think of it like this. In the world of gravity, mass is the star of the show. In electricity, it's charge. Gravity creates a gravitational field. Charge creates an electric field. You see the pattern? And here's the big one, the most important piece for us. The concept of height in our gravity analogy directly translates to something called electric potential. And you already know what we measure that in, volts. Okay, let's really lock in this mental picture. A huge object, like the Earth, it literally creates a gravitational landscape around it. In the exact same way, an electric charge creates an invisible electric landscape. So a positive charge, for instance, makes an electric hill. And if you put another positive charge on that hill, what's it going to want to do? It's going to want to roll right down and get away. So we've got this electric landscape with hills and valleys. But to talk about it, to map it out, we need a word for that electric height. And we've already mentioned it. That name is voltage. So what is voltage really? At its heart, it's just the height of our electric landscape at a specific location. The more technical definition is the amount of work it would take to drag a little positive charge all the way from infinity, from super far away, uphill to that exact spot. So when you hear high voltage, just think top of a really steep electric hill. And this is what it looks like. This is the landscape created by just one single positive charge. That curve shows you the shape of the electric hill. See how steep it is right up close to the charge? That's high potential, high voltage. And as you move further away, the hill gets flatter and flatter. The height, the voltage, just depends on how far away you are. And the unit we use for this electric height, the volt, well, it's named after this guy, Alessandro Volta. His work on the first batteries was revolutionary because it gave us a way to actually create and control these landscapes. And trust me, they can get way more interesting than just a single hill. Over here, you can see the landscape made by a positive and a negative charge together. This is a dipole. It's not just a hill, it's a steep hill right next to a deep valley. Okay, this is great. We can understand this invisible landscape. But what if we could do more? What if we could actually engineer it? What if we could build our own custom hills specifically to store energy? And that brings us to a really big engineering question. If you want to store the most energy possible, you don't just want a high hill. You want a steep one. You want a massive change in height over a tiny, tiny distance. Basically, you want an electric cliff. So, how do you build one? Well, the answer is a device I'm sure you've heard of. It's called a capacitor, and its entire reason for existing is to be a perfectly designed energy storing machine. And it does it by creating a very specific, very carefully constructed electric landscape. So how does this thing work? Let's use our analogy to build one. First, you take a conducting plate and you just pile on a bunch of positive charge. This creates a sort of high, flat plateau. Step 2, you bring a second plate, this one with negative charge, and you put it right next door, super close. What does that do? It creates a deep valley right beside the plateau. And what you're left with isn't a gentle slope. It's that electric cliff we were talking about, a massive difference in potential squeezed into an impossibly small space. And that is the brilliant, simple idea at the heart of every capacitor. By creating this cliff, it can hold a ton of separated charge, which means a ton of stored potential energy, and it can do it without needing some crazy high voltage that would just arc and zap into the air. And we have a way to measure how good a capacitor is at this job. That ability to store energy, basically how much charge it can pack in for every volt of height difference, is called capacitance, and we measure it in farads. All right, for our last section, let's talk about how certain materials behave in this landscape, because there are some special rules. And understanding them leads to some really important, even life-saving, real-world stuff. So what happens if you take a conductor, think of a piece of metal, and just drop it into our electric landscape? Well, the charges inside the metal are free to move around, and they immediately do. They shuffle around to perfectly cancel out any of the hills or valleys inside the conductor. So what's the result? The entire conductor becomes a zone of one single constant potential. It's exactly like dropping a perfectly flat, level slab of concrete onto a hilly field. This whole level ground thing gives conductors some really cool properties. First, because there are no slopes inside, no hills, no valleys, the electric field inside is zero, nada. Any extra charge you try to add to it, it gets shoved to the outer surface. And because the whole thing, inside and out, is at the exact same height, we call it an equipotential surface. Makes sense, right? Equal potential. But here's where it gets really cool. If that conductor is hollow, this effect creates a perfect safe zone on the inside. The charges on the outside surface do all the work, rearranging themselves to completely cancel out any electric landscape trying to get in. The space inside is left totally undisturbed, completely free of any electric field. This amazing trick is called electrostatic shielding. And listen, this is not just some neat physics trick for a textbook. This is the exact reason why, during a thunderstorm, one of the safest places you can be is inside a car. The car's metal frame acts like a hollow conductor. It's a shield. So if lightning strikes, that massive electric charge flows right around the outside of the car, leaving you on the level ground inside, totally safe. So I want to leave you with a final thought. We've just spent this time mapping out this invisible world of electric hills, valleys, and cliffs. The question is, what invisible energy landscapes are all around you right now, generated by the lights in your room, the wires in the walls, the device you're watching this on? Once you learn to see the world this way, you start to see these landscapes everywhere.